Hello, everyone. My name is Tomáš Nosek, and firstly, let me thank the organizers for putting together this conference. I really appreciate the format. I mean, the easy participation and attendance, which I think is really great. Also, thanks for inviting me to give this talk on neutrino oscillation analysis of giant data sets from the T2K and NOvA experiment, which are two currently running long baseline and neutrino experiments. So let's start with motivation for such analysis or why we're studying neutrino oscillations in general. And as you might know, likely from one of the pedagogical talks, leptons mix, and as a consequence, neutrinos oscillate, meaning they change their weak interaction flavor as they travel over particular distance at particular energies. And like current observations are mostly well described by this simple three-active neutrinos model where the connection between neutrino weak flavor eigenstates and propagation mass eigenstates of masses like M1, M2, and M3 as this PMNS matrix, typically parameterized as follows with three mixing angles and one phase delta Cp. Here's sine delta Cp. Uh, when sine delta Cp is non-zero, that would mean that charge parity symmetry is violated in neutrino oscillation and in the lepton sector in general. T2K and NOvA, as mentioned, are long baseline neutrino oscillation experiments, meaning that the ratio of the neutrinos traveled distance or baseline L of a neutrino energy E is about 10 to the power of 2 or 3 kilometers per GeV. And measurements in such experimental setups then have sensitivity to the oscillation parameters of like delta M squared, like the difference between M3 and M2 in squared, and also potentially providing some information on the ordering of neutrino masses, that is, whether the third neutrino mass state is the lightest or the heaviest. Long baseline experiments are also enable for high precision measurements of T2-3 mixing angle and most importantly measurements of delta Cp value. That is whether there is Cp symmetry violation in neutrino oscillation, which might be connected to the preponderance of matter over antimatter in our universe. With that, there is an obvious physics-wise motivation why to combine two such conceptually identical experiments of NOvA and T2K, as their differing experimental setups do have complementary sensitivities. Also, when you decide to join forces in analyzing your data sets, you can design an inter-experimentally consistent framework to report the results on the neutrino oscillation, accessing directly the models and data reconstruction methods of both of your experiments. And finally, as a bonus, you also learn quite a lot of things along the way in the process. Here on the right, these are like T2K and NOvA only results, so confidence level regions for sinus squared theta 2, 3, and of the Cp neutrino oscillation parameters from 2020 as originally presented in Neutrino 2020. So that's a long time back. So the reason I'm showing these is that the joint analysis is based or built upon these 2020 analyses. So one extra aim of the joint analysis is to study this apparent inconsistency in the case of normal ordering of neutrino masses, as depicted here, again be depicted here. Now let's talk about T2K and NOvA in a bit more detail. I mean, experimentally. So these are general experimental setups of both experiments. This is T2K, this is NOvA. Both use accelerators to produce high-intensity muon neutrino beams. T2K uses J-Park facility in Tokai, Japan, and NOvA uses a Fermilabs accelerator complex and so-called NUMI beamline. And both beams can switch their polarity to provide either highly pure neutrino or anti-neutrino beams. And both experiments employ mu detectors to measure the rates of neutrino interactions very close to the beam sources. So then the neutrinos travel over the distance of 295 kilometers in case of T2K. It's the very famous water Cherenkov detector of Super Kamiokande in Kamioka, which is like 50 kilotons of water. And in case of NOvA, that's over the baseline of 810 kilometers to the NOvA far detector, which is a huge 14 kiloton functionally identical detector, in fact, functionally identical copy of a new detector. So that's that. Both experiments use quite a neat trick to get a relatively sharp, narrow neutrino energy spectrum by placing the detectors slightly off axis of the axis of the neutrino beam, so that the neutrino energies peak around 0.6 GeV and for T2K and 2 GeV for NOvA. These different energies come with slightly different relative rates of various phenomenological interaction type, as you can see here. So T2K's interactions budget contains like mostly quasi-elastic scattering, like predominantly with some 2p2h and resonant type of neutrino interaction, whereas NOvA is more egalitarian with respect to all of these types, with also its significant contribution from deep inelastic scattering events. This obviously has to be accounted for by different detector technology and reconstruction methods, and importantly, by methods of energy reconstruction. With different neutrino energies, you have also different baselines to optimize your physics sensitivity to in the oscillation measurements. So what you can see here is the oscillation probability for muon to electron, neutrino as a function of energy for the NOvA baseline and T2K baseline. So that what you can see here is that the impact of individual oscillation parameters, like notably to the CP and the mass ordering, so I know I'll quite differ for each experiment. And as a result, in these simplistic by probability plots of like neutrinos versus antineutrinos at given energy and given combination of oscillation parameters and given baseline, which is experimental specific, you would guess that both experiments probe the parameter space quite differently with different preferred values of the unknowns to maximize the sensitivity to. So combined analysis as like in general has this potential to combine the sensitivities, eventually lifting the single experiment degeneracies where these ellipses overlap, or improving the measurement where there is no degeneracy like here or here. As already mentioned, the joint analysis was based on the 2020 versions of single experiment analyses, these two, and it just got recently out in Nature. So if you're more interested, please go ahead, read the paper. But what does it actually mean in the context of these, let's say, medium-sized but still quite extensive international collaborations to do a joint analysis? I've picked these four general points to describe the whole process of combining analyses, and I have ordered them just by the level of apparent inclusivity, meaning how many different approaches, opinions, and technical implementations, which roughly correlates with the number of different opinions people might have, that you need to consider before you arrive to something you might call joint analysis or intercollaboration. So first, you need a common physics motivation. That's the easiest, and I've been talking about that up until now. So second, you need to come with a mutual understanding of others' experiments, simulation models, techniques, detector technology, and response to the matter of interest, as well as reconstruction, so that you would find out whether you can afford to use these pieces of machineries as they are, or whether you need to replace or unify some of the moving parts along the way. Then you would need to design a common framework accessed by both sides that enables you to reproduce whatever results were obtained by the both of the experiments, which then allows you to perform the actual joint analysis. And lastly, working with many derived inputs created by many individuals across the collaboration, like experts and the like, requires designing a common formal procedure for the overall workflow and its review. So now, as you might imagine, these can be very different within each collaboration and each group. And as a result, you might need to accommodate over a huge set of needs and many requirements in the end. But I won't be talking about these. Instead, let's focus on the second and the third point from the list, which starts with understanding the analysis strategies and deciding how to connect them. So these are neutrino oscillation analysis workflows of T2K on the left and NOvA on the right. So unlike T2K, which employs a forward-fitting technique in a procedure of both, like near detector fit and far detector data fitting, eventually also combined in a large simultaneous near plus far fit, NOvA takes the advantage of its unified detector modeling to employ this new detector data as as a direct correction for its far detector Monte Carlo predictions. However, different these strategies are, they have the very same impact on canceling neutrino interaction and flux uncertainties coming from the new detector part of the analysis. And we decided to interface them somewhere here. Yes, where whenever these far detector predictions are generated, allowing the user of the framework to fiddle with all the knobs entering down here as individual analysis frameworks by Monte Carlo simulation weighting methods. So we have used the original experiment frameworks for Bayesian Markov chain Monte Carlo fitting, that is Mach 3 in case of T2K and ARIA for the NOvA, and containerized and combined them within this, let's say, pinkish interface with each other so that both experimental users would have access to the other one from within their own framework, in this case like Mach 3, in this case like ARIA. And conveniently, in the end, you have consistent statistical inference methods intertwined into originally independent frameworks. And hence, as bonus, you get a rigorous validation through independent analysis streams on both sides of the joint collaboration. So when considering a common model for the joint analysis, we immediately arrived to the conclusion that this is way more difficult than reasonably practical. So instead, we took the path of studying inter-experimental correlations of individual systematic parameters and their expected effect on the oscillation parameters measurements. So we have identified that our detector modeling, that's here, and detector modeling that differs to the level it can be considered basically independent of one another, which also applies to neutrino flux modeling. But for the interaction models or models of cross sections, we went one step further and performed actual simulated data studies to investigate the systematic effects. So we have identified all potential significant systematics for the measurement of delta Cp, theta 23, and delta m squared, and either correlated them if the systematics could be directly mapped between the experiments, as in here for nu mu over nu e cross-section normalization factors, or assessed their overall impact in the measurement. So later we eventually fabricated an artificial correlated systematic biases in simulated data, which these biases way surpasses our usual systematic budgets. And then we did this study when correlating these systematics between the experiments or not correlating, whether that makes any effect. Example of one of the results we can see here. Whereas treating the parameters correlated in this study or uncorrelated have very limited impact on the extracted credible regions of here in delta m squared versus theta 23, imposing an incorrect correlation, which is the anti-correlation that is fully anti-correlate, those just wrong in this simulated case. That can lead to significant biases. So we concluded, given the statistics we were analyzing, the overall sensitivity gains from correctly correlating systematics would be relatively small, and we rather treated most of the parameters as uncorrected. Finally, we can move to the results. So There you can see an example of T2K and NOvA electron neutrino sample spectra with extracted posterior ranges. And this is a table of integrated event counts in the analysis. So it's no big surprise because that was previously published. The first important conclusion here, however, is that the data from both experiments according to the posterior p-values is described well by the joint fit. So no inconsistency among the data sets was seen within the three neutrino oscillation framework, as might have been previously indicated from individual experimental results, but it's not there. For further discussion, let me point out that long baseline muon two electron neutrino oscillation channels, these suffer from this theta 1,3 and theta 2,3 ambiguity, leading to this double peaked structure for the theta 2,3 values preferred by the data. But luckily, the theta 1,3 is very precisely measured in electron anti-neutrino disappearance experiments, the reactor experiments like the diabe, which we can use as an external constraint, limiting the allowed parameter space, like over here, to give a single solution, for example, for theta 2,3. With that, I give you the resulting posterior distributions and posterior credible intervals of delta m squared from the joint T2K+NOvA fit. There is a very weak preference for the inverted ordering that is negative delta m squared, but the preferences are essentially like 50-50. Like, moreover, note that these extracted values have the smallest uncertainty up to date of about 2% in here. The results on the other two parameters of interest, delta Cp and sin squared theta 2,3, are best illustrated by this comprehensive plot with comparisons to individual experimental measurements. So there's a 2D credible regions of delta Cp versus sin squared theta 2,3, and 1D posterior distributions for delta Cp, that's this one, and theta 2,3 conditionally for the case for normal ordering, that is blue, or inverted ordering, that is orange. Conditionally, like if the normal ordering is true, you see the contours overlap just about the right amount to be fairly consistent between the experiment, while the joint fit results into this rather complex structure of delta Cp versus theta 2,3 preferred regions. On the other hand, if inverted ordering were true, that's this region around delta Cp minus pi over 2 is strongly preferred by the data, and delta Cp values of minus pi or 0 lies outside the 3 sigma credible regions. And consistent picture is drawn from Charles-Cox Cp invariant posterior distributions here, moreover robust under certain delta Cp prior changes. And again, if inverted ordering is true, Charles-Cox value of 0, that's here, meaning there's no Cp violation in neutrino oscillations, lie outside 3 sigma credible regions, whereas normal ordering case allows for a broad range of 3 sigma allowed values of J. So, to conclude, we have performed a fit of joint datasets from the long baseline experiments T2K and NOvA, and so both the data are well described within the 3 neutrino mixing framework. We would like to extend this joint collaboration further, as well as we would like to continue with future larger collaborative efforts within the neutrino physics, so I hope we can look forward to seeing more inter-experimental analyses and results in the near future. So thank you for your attention. That would be all from me.